Okay, next half of the paper. This is March 2023, paper 429702. Look at the question number 6. The question is, a Hall probe is placed in a magnetic field. The Hall voltage is 0. The Hall probe is rotated to the new position in the magnetic field. The Hall voltage is now maximum. So initially it's 0 and then it becomes maximum. And the question is, explain these observations. So we will write here when the plane of the probe is parallel to the magnetic field. So no magnetic field, no magnetic flux is cut. Thus, EMF induced or the reading is 0. There is no deflection of the charge particle. So the reading is 0. But when the plane of the probe is perpendicular, according to Fleming left-hand rule, forces experienced by the moving charge particle, it's deflected. So due to this maximum flux cutting, the reading is maximum. So when the plane is parallel to the magnetic field, no deflection. So EMF, the Hall's voltage is 0. When it is perpendicular, then maximum deflection. So Hall's voltage is maximum. Then the formula for the calculating the Hall voltage is given VHBI over NTQ. B is magnetic flux density. I is the current. N is the number density. T is thickness, not the time, and Q is the charge of the particle. Now the material given, silicon and copper, number density given. And the question is, state the meaning of N, small n. This is actually the number density of the charge carrier. Mean it is the number of the free electrons, number of the charge particles per unit volume. The number of the charge particle per unit volume is called this number density. Next question, explain why the Hall probe is made from the silicon rather than. Look at the silicon number density. Its number density is small, and its copper is maximum. So according to the formula, this VH is inversely proportional to N. So when the number density is small, the Hall's voltage produced will be maximum, which will make the Hall probe more sensitive because a large value of the VH Hall's voltage will be produced. So to make the Hall probe sensitive, this number density must be small because VH is inversely proportional to this N. Next, the Hall probe gives a maximum reading of 24 millivolt when it is placed in a field of 32 millitesla. The same Hall probe is then placed in a magnetic field of a fixed direction and varying flux density. The Hall probe in the next position is in a fixed position so that the angle between the Hall probe and the magnetic field is the same as when the Hall probe was 24 millivolt. The variation of the reading VH on the Hall probe with time t 0 to 8.61. So look, this is the Hall's voltage and this is the time. So 3 portions of the graph. This is positive gradient, then this is 0 gradient, negative gradient, and this value is maximum. Now the question is, a coil with a 780 turns and the diameter of 3.6 centimeters placed in a varying magnetic field. The plane of the coil is perpendicular, meaning the angle is 90. Calculate the magnetic magnitude of the maximum EMF induced in the coil between 0 and 8.6. So first, the Hall's voltage produced here is 36. And we have information, if the Hall's voltage is 24, magnetic flux is 32. But our Hall's voltage is 36. So for 36, we will calculate first the strength of the magnetic field. So 24, then it becomes 32. When the voltage is 36, unknown, so the X becomes 48 millitesla. Mean for this 36 Hall's voltage, the magnetic field will be 48 according to this rule, unitary method. Now, we have to calculate the maximum EMF. EMF is minus NBA over T. N is the number of the turns. B is the flux density. A is the area. And T is the time. So the number is given 780. Then area is equal to pi by 4 diameter square, or you can use pi r square, but pi by 4 diameter square, because the diameter is given in centimeter, 3.6 10 power minus 2, and then square. And then B, magnetic flux density, we have calculated 48 millitesla, so 48 in 10 power minus 3. But for the maximum EMF, the time must be small. For the maximum EMF, the time must be small. So we will look at the small time in which the flux is changing. So here the flux is changing, or the voltage is changing for this 3.2. And here it's changing from 3.2 to this 8 point approximately 6. So this distance, this time gap is 1.4. So we will use this time, which is small. So the change of this is 1.4. Time change is 1.4. So we will use here 1.4. So after calculation, your answer will be 0.027. So do remember, for the maximum EMF, we will take the short time in which the EMF is changing, that the flux is changing. And the next, number 7, is a beam of the white light passes through a cloud of the cool gas. The spectrum of the transmitted light is viewed and they contain a number of the dark lines. Explain why these dark lines occurs. I mean, we have to explain line spectrum. Now, photon of light is absorbed by the orbital electron of this gas. Usually it is hydrogen gas. Energy of the absorbed photon is equal to the difference of energies of any two energy levels. I mean, energy of the incident photon, or the photon which is absorbed by the hydrogen, exactly equal to difference of energies of two energy levels. That's why all energy levels and all photons in the universe are discrete in their values. And then after the absorption, electron will excite to the higher energy level, and energy of each photon has a single wavelength, which can be calculated by using this E is equal to hc over lambda. When the excited electron de-excites its ground state, whole of the energy is emitted in number of the photons in any possible direction, so which leads to the dark lines. So after absorption, electron excites to the higher energy level. Energy of each photon has a single wavelength, E is equal to hc over lambda. When excited electron de-excites the ground state, an energy photon is emitted for each jump. There is a single photon is emitted. Okay, so the single photon is emitted, any energy photon is emitted, an energy photon is emitted in any possible direction. So one jump will emit one photon. Next, some energy levels for the electron and isolated hydrogen atom are illustrated. Table 7.1 shows the wavelength of the photon that are emitted in the transition to N2 orbits. So these are the wavelengths given. The energy associated with the energy N2 is minus 3.4 electron volt. And calculate the energy of level N3. So this is the journal formula. Energy of the orbit, energy of the energy level is K divided by energy level square, number square. So the second energy is 3.4 electron volts given, K constant, and N is 2 square. So this constant is 13.6. Now we have to calculate this. And 3, energy of the third, K divided by N square. K is 13.6. The number 3 square, so it's coming 1.51 electron volt, but we have to convert this in joule. So 1 electron volt is 1.6 10 power minus 19. So the final answer is 2.42 into 10 power minus 19. Next, number 8. Plutonium-238 is unstable and undergoes alpha decay. Complete the equation to show the decay. Look, this is alpha. This is alpha is 2, and this must be 4 then. It means the proton number of this plutonium decreases by 2 due to the emission of the alpha. So this U becomes 92, uranium 92, and this mass number decreases by 4. So the mass number of the uranium will be 234. And the next, the power source in a space probe contains 0.874 kg, mean 874 gram of plutonium-238. Each nucleus of the plutonium that decays emit 5.59 mega electron volt, mean after single alpha emission, after one nucleus decay, this is the energy released. The half-life is given 87.7 years. Calculate the initial number. Look, this is the formula. Number is equal to the mass in kg divided by molar mass. Now, the mass in kg is given 0.874, and the molar mass is 238 U, 238 U. And the value of the U is 1.66 10 power minus 27. So after calculation, you will get N naught 2.21 10 power 24. This is the initial number of plutonium. Next is determine the initial activity of the force. Give your answer. Units for the answer. Activity is equal to lambda n. And do remember, this lambda decay constant is 0.693 over half-life. This 0.693 can also be written as ln2. So 0.693 divided by period is 87.7. But these are the years, 365. So they are converted into days, into hours, 24, into seconds, 3600, multiplied by n, initial. So after calculation, you will get this answer 5.54, 10 power 14. So when this period is converted into seconds, then the activity is in backward because 1 over second is backward. Next, use the answer to determine the initial power output from the source due to the decay of the plutonium. The power is equal to total energy divided by time. And the total energy is equal to energy of one reaction multiplied by total numbers of nuclei divided by T. But N divided by T is called the activity because these numbers are decaying per unit time. So the number of nuclei decaying per unit time is activity. So the formula for the power will be activity times energy of one decay. So activity we have calculated here, 5.54, 10 power 14. And the energy is given 5.59 10 power 6. And it is mega electron volt. So 1 mega electron volt is converted into joule, which is 1.6 10 power minus 13. So answer is coming 496. This is watt for the power. Next, the space probe will continue the function until the power output from the plutonium in the source decreases to 65.3 of initial value. Look, this process is spontaneous, random, exponential. So we will apply here the exponential relation. So P over P naught is equal to e power minus lambda T. This P over P naught ratio is given 65.3%, mean 0.653 E, and this lambda is 0.693 over half-life, multiplied by time. Now, after calculation, ln of 0.693 multiplied by this value, 87.7 this, you will get this 53.9 years, approximately 54 years. Because this half-life is a given year, the time will be calculated in years. Next, an alternative power source uses energy generated from the radioactive decay of polonium-210. This isotope has a half-life of 0.78 years, very small as compared to the plutonium. The mass of the isotope needed to same initial power is 3.37 gram, very small mass. So just one advantage, one disadvantage of polonium. Look, advantage due to small mass, less energy, less work is done to move it in the space in the required position. So due to small mass, less energy is required to get probe in the space. I mean, less work is required. And disadvantage, it has very short half-life, so it runs down quickly, so it cannot provide energy for the longer period because it runs down quickly due to the shorter half-life. Next, question number 9 is, ultrasound is used to produce diagnostic information about the internal body structure. Explain how ultrasound is are detectors. Look, this is sound. It has compression, rarefaction. So sound wave has compression and rarefaction, which causes vibration in the piezo crystal due to pressure difference. When ultrasound strikes the surface of the piezo crystal due to pressure difference, due to compression rarefaction, there is work, and the work is done on the charges of the crystal, and the piezo crystal is made of silica oxide, silica positive ion, oxygen negative ion. So when work is done on the charges of the crystal, voltage is produced, EMF is produced, so it's detected. Next, alternating voltage varies with time t according to V is equal to V naught sine omega t. The voltage applied to the ultrasound probe, RMS value is given 66 volt, and the frequency given. Look, this is the peak value. And here we have to calculate the peak value. Look, RMS is equal to peak voltage divided by under root 2. So 66 multiplied by under root 2, 93. This is the peak voltage. And this theta, sine theta. Theta is omega t. So omega is equal to 2 pi f. Omega is 2 pi f. Omega is required, 2 pi value, and the frequency is in mega, 4.3 into 10 power 6. So we will get omega 2.7 10 power 7 radians per second. Next, this table is given for air and soft tissue, density, speed, acoustic impedance. And the question is determine the unit of acoustic impedance. Look, Z is equal to rho V. Rho is the density, and this V the speed. After simplification, we can determine this kilogram meter power minus 2, second power minus 1, unit for the acoustic impedance. Calculate the density. Acoustic impedance is density multiplied by speed. So density is acoustic impedance divided by V from the table. So the soft tissue acoustic impedance is 1.7 10 power 6, and the speed is 1600. So the density is 1100 for this soft tissue. Next, use data to explain why the ultrasound cannot be used to produce the image of the air. Actually, transmission of the ultrasound in the patient body depends on differences in acoustic impedance. So here, look at this, huge difference, 10 power 6, 10 power 2. So due to this large difference of the air and the soft tissue acoustic impedance, majority of the ultrasound intensity is reflected back. Very small will be transmitted, so which is not sufficient, which is unable to produce any image. Thus, the maximum intensity of the ultrasound is reflected back, so no imaging possible. Because negligible transmission, almost 100% intensity is reflected back. No transmission through the medium, so no imaging. Now, the next is a student observes different stars from the Earth. Give 2 reasons why some stars appear brighter than other. First is definitely this star is closer to the Earth, so brighter because it is closer to the Earth. And second, it's brighter because it has large luminosity. State what is meant by the standard candle. Any object in the space which has well-known luminosity is known as standard candle. A spectral line from the star within the galaxy is observed to have a wavelength of 660.9 nanometer. The same spectral line measured in the lab is observed to have a wavelength of 656. So actually, that light is giving this one, but due to redshift, wavelength increases, so we observe this. The question is, show that the speed of the star relative to the Earth is 2 point. This means recessional speed. So the formula is the speed is equal to change in lambda divided by actual lambda into speed of light. So this is the change of lambda, and the actual lambda is smaller than this observed, 656.3 times speed of light. You will get this answer, which is 2.1 10 power 6. Is proved. Calculate the distance to the star. The Hubble's constant this, and the Hubble's law is V is equal to H naught D, and the D is equal to V over H naught. V is calculated and the Hubble's constant is given 2.310 power minus 18. So the answer is for the distance is 9.110 power 23. Next is state and explain what can be concluded about universe based on the change in observed wavelength. The wavelength of light coming from the distance object is increasing. So the wavelength of the light is increasing from the star observed from the Earth. And this increase in wavelength is called redshift phenomena in Doppler's effect. And in the redshift, the object is moving away from the observer. So the galaxy or the star is moving from the observer on the Earth, from the Earth. Thus, the evidence is universe is expanding, which is called the Big Bang theory. So this is the paper.